Okay, so far we learned how are those physiological perspective, like a sensory feedbacks involved for the human movement control, like um, motion sensor, vision, vestibular organ, muscle spindles, and its sensory information pathway, neural pathway to the brain, etc. For now, we are going to then formulate how our control engineering control perspective can be implemented to understand the human movement. Very one simple example would be a posture control, because the upright posture is engineering perspective is inherited unstable system, inverted pendulum, and how those are controlled based on those sensory feedback. To show the evidence that the posture control, upright posture, uses those sensory information, what would be the best way to show it? Well, if you use those sensory information, if you disturb the sensory information, your postural response will change, right? So that's what we are going to introduce as a sensory organization test, SOT test. So this is the equipment developed late 80s to examine the patients who has a balance or disorder, especially the vestibular disorder. And this is equipment is composed by the one measurement system from the bottom, like a bi-pulse force plate, measuring the central pressure for the subjects, their sway, body sway back and forth. And there are in three wall environment, okay, that covers the visual field of the subject. Okay, so the motor controlled platform moves its plate back and forth and its environment back and forth. And then to make a subject safe, there is a safety harness. So this is designed to manipulate the sensory conditions for required for posture control. So we know that the vision, vestibular, and somatosensation, or the muscle proprioception, muscle spindles, are used to give body measurement information to the brain, right? So among those three big category, this system is manipulating the vision, eye, and the ankle proprioception by manipulating the surface. So the conditions, okay, let me show this way. So the vision, there are just regular normal vision, and there is eyes closed condition. Okay, so no more vision information. And those environment that covers the subjects will move with you. Okay, it's a sway called sway referenced vision. So even though there's a vision information coming, those informations are not really reflect how you move, right? The false sensory information per se. How about the support surface? There are three conditions: has a fixed surface, firm surface. So your ankle proprioception, ankle spindle information is true, is actually reflecting your body motion. For those other three conditions, the surface is moving with you, like a moving sway reference. So if you lean forward, your surface is tilted forward too, so that your ankle proprioception, ankle spindle, does not give you the actual movement, right? That with respect to the earth. So for those six conditions out of three available sensory information, condition 2, only vestibular and spindle available. Condition 3, well, 3 sensory information available, but the visual is not true. Vision is not correct information. In condition 4, the spindle information is not correct. Condition 5, vision is off. So you only have 2 sensory informations available, but one of them is not true value, not a correct value. And for condition 6, there are 3 informations available, but 2 informations are distorted. So these are the conditions. And then what would you expect? Would you expect to change the significant change for the sway? That means you require those sensory information for the posture control. The data show that there are huge increase for the sway in condition 4, 6, and 5. So this, by having this experiment and then measuring the sway quantitatively, we can actually estimate sensory contribution for the upright posture control and upright balance. So that's the one example for how those sensory distortion will affect the behavior and telling us those sensory informations are used for posture control. Okay, so since we have an evidence that sensory informations are used for posture control, the balance control, the next step is we are going to, establish the control approaches or control disciplines used to describe the human posture control or understand the human posture control. So I'm going to set the hypothesis like for the upright posture control, I have to do the apply the joint torque to maintain a balance, and those torque is based on the state feedback. State here means for joint kinematics. Okay. So to support this hypothesis, we should obtain the data because this is a really well controlled system like a human body, and I want to identify the control. So I should make the situation that control is necessary. So I should actually perturb the upright posture. Okay, there are many ways to perturb the posture, such as I can actually push the subjects front and back, or I can actually move the support surface back and forth, or the other possible physical perturbation could be possible. And for that perturbation, the subject should actuate the joint torques to maintain a balance. If I collect the motion data and joint torques data, I can figure that out what kind of control human use for the posture to maintain a balance. So so you should actually design the experimental protocol. Here, I should design the perturbation, how and why, and then what value should I use. And for human study or for animal study, once you design those experimental setup or design the protocol, you should get approval from IRB, Institutional Review Board, if this experimental protocol is valid and then approved. Okay. And then to avoid human habituation or adaptation to a specifically repeated perturbation, because usually when we run some human experiment, we actually collect the data multiple times. So we apply the perturbation repeatedly so that the subject could easily adjust to them or adapt to them. So try to randomize the order of the stimulus if possible. And generally, like the measurements are kinematics and kinetics. Kinematics using the motion capture system, and kinetics using the ground reaction force plate. And those information could be used to calculate the inverse dynamics joint torques and joint force through the inverse dynamics, what we have learned in chapter 1. Okay, so also one thing I'd like to note is for perturbation design, you should actually refer to the human study related articles, or you should actually do the observation, because sometimes some specific perturbations may lead to a specific response. Okay, if you want to examine the general response, you should be cautious about designing the perturbation. In engineering wise, suppose that you want to analyze the vibration of the structure, and then you should avoid applying the impulse input to the nodal point, right? Similar to that, when you design the perturbation, you should be cautious. What would be the those perturbations will generate the responses. Also, once you find out the joint torques and kinematics relationship, you should figure that out. Which gain you are not actually the control designer. You are not choose the gain. You should identify the gain. Okay, you should identify the gain, feedback gains of the human movement, and instead of having the closed loop holes design, you have no option. It's already there. It's already the human movement has its well controlled closed loop pole behavior already. So you should also examine what would be the benefit, okay, of those control behavior for the human movement. Those are the questions that you should ask for studying human movement control mechanism or control perspectives. Okay, I'm going to summarize then how the posture control solution steps look like. Okay, the very first step, even though it's a walking, running, passive, active, you should always start with the equations of motion. Okay, so either you would do some double inverted pendulum to describe the human posture or single inverted pendulum. No matter what, the very first step is you should start with the equations of motion. Since we are examining the controlled behavior, you should specify the T, the joint torques actuation. And then remember that for the previous chapter, we assume that this is a muscle activated control. Like muscle, the joint torques is a function of muscle force. So using the Hills model, it was a function of joint angular velocity, right? Joint angular velocity in a reciprocal manner. In this chapter, now instead of using those Hills model, I'm going to use the state feedback model. So joint torque will be proportional to joint kinematics, okay? So previously for the dynamics dominant problem, we have to solve the dynamics until collision for the walking or takeoff for the running or jumping or release for the throwing. But here, issues are we have to formulate the T, because this is what we assume. This is a state feedback. So we should specify what kind of formulation will explain the state feedback for the human corresponding human movements. Like what would be the joint torque? Is it gonna be a full kinematic feedback, or it's gonna be a reduced order state feedback? Those are the one that you have to set in the very beginning. And also to calculate the joint torques, you should do the inverse dynamics. Okay, again, once you formulate the T, the state feedback control for the joint torque, next step is you have to identify the gain. Okay, so either maybe you can do the regression or the forward simulation or the other various way to reproduce the data or to represent the human data. You should identify the K. Once you identify the K, the next step is, in terms of control perspective, of course, you should examine the closed loop dynamics, right? Once you set the gain and then you run the closed loop dynamics are satisfiable. So in this case, it's not like satisfiable. It's because you are not designing the controller. You have to see if your closed loop dynamics look similar to the human behavior, human data, or feasible, like this behavior could be achieved by human. So you should examine the closed loop dynamics, and also if your control model for the human motion could show you a pretty decent behavior explanation, you should also check, is that stable? Okay, is it stable, guaranteed, or it's robust? Okay, if you change the gain a little bit, does that really like change the response much, or doesn't really change for the body parameter changes? That was usually the error comes in, the part that error comes in. So you should examine the closed loop dynamics, and you can also do the parameter study similar to what we have worked on for the other human motion analysis. And this is a brief outline for posture control solution steps.